Hi, welcome. My name is Liona Fan-Chiang. You're joining us for week 3 of the course on Kepler's new astronomy. And today we'll cover the second half of book 1. For those who are not familiar with the book is separated into 5 parts. And the first part is a setup, but also a setup to a refutation of all that has come prior. So all of the different theories that have come prior to Kepler, as a way to preface Kepler's introduction, his proof, his elaboration of a truly new astronomy. And the last time you found out that Kepler's uniqueness, one of Kepler's uniquenesses, is that he is adamant that we should reckon things, not just calculate things, but we should consider motion from the standpoint of something real, and specifically the sun, which means, of course, that his predecessors used something put at the center of their universe, including Copernicus, something fictional, which they called the mean sun, the average sun. So for those people who did their homework, you're supposed to read through chapters 5 and 6. And these two, as you might have seen from the very, very last paragraph of the whole book, at the end of chapter 6, these two are the hardest chapters. And he is very, very rigorous, and for good reason. He is about to overthrow current science as it is. And we were just discussing it here. It's sort of like if you came into the room and you said, "Orbits are square," people look at you like, "You crazy, get out of here, you heretic," and so on. You better first prove, one, why the current theories don't work, and then have a pretty good proof of why you would come out and say this thing. So Kepler has to first take on the difficult challenge of refuting all that has come before him, so thousands of years of so-called astronomy. So I want to review a few things from last time, which may have not been that clear, but are very crucial for this section. And with regard to what Kepler calls the first and second inequalities. And I guess, why don't we start with this? Who can tell me, at least from your understanding, what the first and second inequalities are? Anyone want to take a guess at that? Don't worry, there's several right answers. Yeah, I can hear you.
Okay, so the first inequality is the fact that the planets are not going at the same speed at all times.
Okay, want to take a shot at the second one?
The second one is the fact that you have the retrograde motion happening at different times, acting not specifically.
I barely hear you, Daniel.
No, I think it's Luke.
Or Luke, whoever. I can't even tell.
So, could other people hear him? Oh, that's Luke.
No, not very clearly.
Okay, I'll just repeat what I think he said. He said that the first inequality was the fact that the planet does not go around in equal speeds all the time. So it does not, either the the planet does not go around the sun all the time in equal speeds all the time, or around the Earth. Then the second inequality, I think you said, was the fact that the planet Mars, for example, goes into retrograde motion, stops at some certain point and goes backwards. Is that a good repetition of what you said? Okay. Yeah, that's exactly right. And there's the reason I said that there's several right answers is Kepler himself poses it in several different ways. One of the ways is he calls the first inequality the zodiacal motion, because it goes the planet must go around through all the zodiac according to the sun, or according to the mean sun, either way. And he calls the other one, the second inequality, the one you said is seen by this retrograde motion, that which is tied to the sun, has a relation to the sun. We can see that for some reason it always occurs when the sun has a particular relation to the Earth and the other planet, and specifically at opposition. So when the sun, or the mean sun, is on one side of Earth and the planet is on the other, that is always when this retrograde motion occurs. And throughout these last two chapters, Kepler is going to put in the sun. So he's already, over the first four chapters, he showed that he went through this slightly long process of showing that all of the different hypotheses, whether it's Earth-centered, whether it's so-called sun-centered with Copernicus, and so on, they were equal. And he said at a certain point that, well, we need to see now what the effect is if you put in the real sun and not just some fictitious point that happens to actually be the center of Earth's orbit. So for all of chapter 5, he wants to take on just the first inequality. So that's just the changes in the planets, in this case Mars's orbit, were it not to have this, whatever causes this retrograde motion. And the way that we've been able to get around that is to look at specifically the points of what we call opposition. And I should have pulled, I think I have this pulled up. So points of opposition are when, like I said, when the sun is on one side, the sun is on one side and the planet is on the other, and it's the only time when what the Earth sees is also what the sun sees. So if you take those observations continuously, I'm going to try to pull that up right now. If you continue to take those observations, then as the observations circulate around the whole orbit, you start to get what the sun actually sees throughout the whole orbit. And what I'm doing is I'm pulling up, and I'll show you in a second, I'm pulling up the part 1, chapter 5.
You can't promise something. I have no idea what you're
Somebody is not muted.
ask what you're going to ask, and then naturally respond.
Let's find out. Okay. I think that worked. Okay, so here we go. hopefully people can see that. So it's a great animation. It actually shows something else, but it also serves our purpose. Okay, so by taking these points, and we'll just wait until the animation comes back to the beginning for a second here. So this animation is going to show, okay, so it's marking a couple of things, but primarily it's marking when the Earth and Mars is lining up with, or I guess, yeah, is lining up with the Sun. And with this, people were hopeful that that we would get a true view from the Sun of what the planet's motion was. Now, what Kepler wants to do is he wants to introduce the real Sun. Now, people have been using this mean Sun for quite a long time, and when Kepler brought this up to Ptolemy that we should use the real Sun instead of just some fictitious sun, Ptolemy had 4 years before this, before the writing of this, had said, before the writing of the New Astronomy, had said, well, there's really no use because for the first inequality at least, the mean Sun serves perfectly. It looks great. And what this animation is actually showing, so the yellow dot is the real Sun. The blue dot is the center of Earth's orbit, which is what Ptolemy, Brahe, and Copernicus have used as the Sun. And this animation shows the difference in what they actually see as opposition. So you'll see that when you zoom out that there is a difference. The two, the mean Sun and the apparent Sun, will see different zodiacal signs or different stars behind Mars. And they will also take different days or different points in which Mars is technically at opposition. So this poses a couple of different problems. One, Kepler wants to show that putting the apparent Sun in is still going to give you the correct, the good measurements, the measurements that are correct. He wants to show that, okay, fine, you showed that using this mean Sun works. I'll show you that it's very close to what is reality. That's what he wants to show in this chapter. And he's going to fidget around with what the orbit should be, such that that's the case. And we'll look through that. So again, he wants to be able to show that this mean hypothesis, this hypothesis with the mean Sun, is very close to what's actually occurring, which is a planetary system. He wants to pose it's a planetary system which is based around the real Sun, that is driven by this hot fiery ball in the sky. And he says, I think it's in this chapter or the next one, he's almost ranting. Why is it that that Ptolemy and Copernicus and whoever is posing epicycles can think that it's okay to have planets concentrating on points that don't exist and that are supposed to guide their motions? Okay, so I hope that's clear. Let me switch back here. Okay. Okay, so I'm going to go through a couple things, and I hope it's not too confusing.
Hey, Leona.
Yeah.
Hey, just real quick. when they use the apparent opposition,
Mhm.
I mean the mean opposition, because I know with like the apparent you would use the sun and the Earth, the position of the Earth and the sun and Mars. But with the mean sun, what replaced the Earth? So if they use the Earth's position and Mars, then what was Earth if they're using Earth already? It's just how the Earth sees Mars, and they call that opposition.
Yeah.
That,
Whoops. Somebody is.
I think it was just the
Was
when they were
them?
unmuted.
Okay.
Yeah.
Yeah. So right, Earth is where it is. The only difference is the mean sun. So, if I understood your question right, so Earth is where it is, but instead of taking this achronical position, so actually doing the observation of where the sun is and when it's directly opposite the planet Mars, they're taking a calculation, basically. A calculation of, it's actually a calculation of the Earth's, it's the Earth's center. It's an average sun. So if the sun were to go around us exactly, constantly, and were to traverse the 365 days in equal speeds all the time, either the center of the sun of that type of sun, or the center of Earth's circle, depending on whose system you're looking at, is then what they're using. So it's a calculation. There's actually no observation being done. A calculation on the sun's part, and then you're observing Mars. Is that clear?
so it's like, it's just if the sun were to move uniformly, and then just that motion, and then where Mars is and where you are. So it's like, it's just purely on paper. There's no observation. Right?
Not for the sun.
Okay.
And the observation is a difficult observation. I mean, you know, to do the, I'm not exactly sure how I'd like to see exactly how they did it, but even the achronical, the sort of sunrise, sunset. So either when the sun is setting and the stars rising, or the stars setting and the sun is rising. That is one way. I don't think that's how, I actually don't know how Kepler did it. Maybe Jason knows. Because Kepler did do some. One of the things that'll come up, actually I think it comes up pretty near the beginning, is that Copernicus uses the mean sun because all these opposition measurements done by Brahe are relative to the mean sun. So it's sort of a convenience as well. But the inconvenience for Kepler is that if he wants to make this new system, and he wants to see if all of these, the old systems work with the apparent sun, he needs observations from the real sun. And so there's a couple of things he can do. He could take his own observations, which he does take a few. And the other thing he could do is he could adjust them. And the one thing about Brahe is he was very meticulous. And so he took a lot of measurements. And so in that sense, Kepler was able to do some form of zeroing in on where the real sun might have seen real opposition, where the sun, Earth, and Mars actually were aligned. In some cases it was a couple days before, a couple of days after, and then, you know, if a couple days before, then since the Earth is going faster than the sun, the stars behind Mars will be different. In other words, the longitude will be different. So that is also a problem. And you'll see in the second book that he's very meticulous about choosing, Kepler is very meticulous about choosing which observations to use, which can be used for this. which he was able to adjust or he was able to measure himself. I did realize also that, and maybe, anyway, I realized also that during this chapter that since, actually, I'll get to that in chapter 6. What I want to go through now is some of chapter 5, and I hope I don't lose people. If I do, it's okay. We'll go through it again. Okay, so here's what he does. I'm going to switch over, and hopefully this works. Okay, people can see this? So let's take an orbit, and here's the center. This is Mars's orbit, for example. Here's the center of Mars's orbit. Let's take this as the sun. And this is Mars's equant. So this is the point where if you stood here, Mars would be going at exactly the same pace all the time. This is the sun. And here, let's put here the mean sun. And again, Kepler wants to show that these two, that he can make a system that's visibly accurate, whether it's from the sun or from the mean sun, because he knows that it is. I mean, he knows that what Brahe said, at least. He wants to prove what Brahe said. And then he wants to be, eventually, at the end of this, he wants to be able to take the system that is imperceptibly different for the first inequality and take it to see if it's also imperceptibly different for the second inequality. So here we go. And just butt in if you really get lost, because it's not that easy. Okay, so here's the first thing he tries. So he says, okay, normally, here's a line of apsides. I guess I could take a different color. Is red too egregious? Okay, so here's a line of apsides, the one in the middle. And he said, okay, well, let's try this. Oh, first, okay, so the line of apsides means that the, since at the equant, it's always going to be equal, right? The motion is always going to be equal, meaning that this arc right here is going to take the same amount of time as this arc here. And you can see that this is the top one is much smaller for the same amount of time. So this one is the slowest point. And here's the fastest point. So that's what defines the line of apsides, which is this middle point here, middle line here. Now, that's real. That's the one that we want to find. That's going to define sort of the shape of the orbit. The orbit's physical shape is circular, but its motion is really, it's determined by this, which is the slowest and fastest points and to what extent they're slowest and fastest. So he says, okay, these points are physical. But when you move off of the center, when you're moving, for example, when you're not at the sun, but you're over here at the mean sun, you get something different. So let's see here. Color. So okay, if you take the mean sun, and you've done this before, so you ever notice that when you're driving, things that are close to you are moving a lot faster.
Mm-hmm.
So the things that are the furthest away, like for example, for the mean sun, it's this point, is going to be slower than everything else. So Kepler says, okay, that means that there's a physical point which is the slowest, and then there's an optical illusion which has an increased slowness due to the optical illusion. And so therefore there's some middle point at which you actually perceive from the mean sun the slowest point. Oops. And it's not at the physical point. It's sort of inched over because of this optical illusion. So you say, okay, this is a problem. Well, yeah, this is a problem because this is not what Brahe had said, at least, which is that the mean sun works just as well as this other sun, the sun. Okay, so he's gonna mess around now with a couple of different hypotheses. Okay, so her first hypothesis is let's just make the physical line of apsides, the one that used to be here, just over here, where the optical one is. That'll solve our problem, right? So he puts the equant over here, the new equant. Says, well, that's a problem because you're just changing the actual physical motion. That sort of defeats the purpose. You want to show that it's observed differently, not that it's actually different. So that doesn't work. His second hypothesis then is this: is to then take a new line of apsides through the equant. So he says, okay, if it's the equant, hold on a second. Okay, yeah, so if the equant is in the same place, then, you know, this is still going to be the slowest. This is the physical, I mean, in other words, the equant is in the same place. To the sun, nothing is changing. So, but if the line of apsides is over here now, we got to change something else, which is seemingly radical. Which is now we've got to, you know, make a new center.
Okay.
So this is now the new center. It's over here. And new center means new orbit. So sort of has this radius. I think I might be able to, that's fine. Okay, so turns out to be, you know, it's edged over like this. So I'm just going to draw in my not so perfect way the new orbit.
Pretty good.
Okay. So that's a new orbit, and it's, you would think that that would make a huge difference. You had a new orbit. But he shows that actually it makes less of a difference because, as I said, the equant is still in the same place. According to, equant is still looking and doing the same thing, right? So if you were standing at the equant, all of the motion of the planet is going equally at all times, constantly, and so on. And the sun is going to be seeing that same thing. Now, the question is, is there a big difference? And if there is a big difference between what the sun sees and what the mean sun sees, where is the biggest difference? And that we want to figure that out because we want to see if this is correct, if this is a fine model to use. And so he finds out that he reasons that the biggest difference is going to be right here between these two hypotheses. Right here. That from the mean sun, and here's the thing I want to point out is that you might have not got it from the pedagogical online, but in the book, Kepler is he phrases it like this. He's phrasing it basically like the sun was always there. Now you're just moving. You're moving the sun. So it's not that he's introducing the sun. It's if you were to introduce a mean sun, what changes are you actually introducing? I don't know if that is clear as far as how that is differing. It's not a big deal right now, but I found that interesting. So he finds out that this angle from the mean sun, we're to see this new orbit versus the old orbit. This angle would be a difference of 4 minutes and 24 seconds. Now, this is very, very small. Anybody remember how much a minute was last time? From last time?
1/60th of a degree.
Yep, it's 1/60th of a degree. People know a degree is it's pretty small. Let me see if I can get back here. Okay, so it's pretty small. Last time, I think it's in I forget where it's written, but Jason had brought it up at a certain point. It's a piece of lead, so it's a 0.7 piece of lead held 8 feet away. Pretty small. It's so 4 of those. 4 minutes. It's smaller than observational accuracy, especially at that point. So at this point, Kepler has come up with a system that is totally equivalent to, well, I guess it's the other way around. He has made a system for Ptolemy, Copernicus, and Brahe that is totally equivalent to what he thinks is a more true system. Okay, so now we're going to go on to chapter 6. Are people confused at this point? Say no.
We're a little bit confused, but no questions just yet.
Okay. Okay. Well, it's okay. The main important thing is the conclusion. I mean, there's very fun, interesting things, and if it were up to me, I would have asked you guys to read the whole chapter, but it's not. It would have taken you a day, which is how long it took me. But it was very fun. So I'm going to go on to chapter 6, and then we'll come back and see if it makes it clearer. Okay, so come back to this. Oh, geez. Okay. So like I said, Kepler ends up with this hypothesis. So this The black one being what he thinks is more correct, based around the apparent motion, and the blue one being what Ptolemy or Copernicus might have come up with, according to the mean sun, which would have given them a perfectly fine tool for figuring out or calculating the first inequality. Now we want to see if this is okay with the second inequality. So, what happened to my toolbar?
You have to, the screen is blocking. You have to move down the whole screen.
The whole screen?
Yeah.
Oh, this thing? Oh, I see what you're saying. There we go. Yes, you're right. There it is. Okay. Okay, so okay, so the second inequality. So the second inequality, Kepler says it right away. You know, Ptolemy has this funny account of the second inequality, which is he has these epicycles, right? And they account for the backwards motion, the apparent backwards motion. But this is, yeah, right. And Kepler says he agrees with Copernicus on this one, which is that, in fact, the second inequality comes from not the motion of Mars, but the motion of Earth. And that is introducing this mixed motions. So you have Mars, which is going around on its business, and then you have how we see Mars, which is then mixed into the motions. And he says there's a couple of things. So say we're here. Here's Earth. We're going this way. And okay, I'm going to take two positions, and you're going to tell me what the difference is. Here's Mars going this way, and here's Mars.
We don't see it yet.
Oh, you don't see anything?
All we can see is you.
All right, I'm gonna back up a couple then. So, okay. So here, the big one here is Mars's orbit. You see this now, right? Here's Earth's orbit. And, okay, so let's say Earth is here, and Mars is in two different places at different times, okay? So Mars is over here, so Earth is going this way. And at some other point, Mars is over here. Which one, the upper one or the lower one, does Mars look like it's going faster? From us, from Earth.
Closest one.
Yeah, the lower one.
Why do you say that?
When things are closer to you, they appear to be going faster.
Okay, but what about the direction?
The direction.
People out there have an answer?
It changes its direction faster as it gets closer to us in relation to where we see it.
Okay.
We think it's the top one.
Why do you say that?
Okay. Not all of us do.
I think it's the bottom one.
I changed my answer to the top one
Why do you say that?
because they're traveling together on the bottom,
Yeah.
and so as the Earth, since it's in a smaller orbit, the Earth is going around, and then Mars will appear to be slowing down and going backwards.
Uh-huh.
From our point of view, as we're looking at it, as Mars starts to catch up as it's coming around.
Okay. Yeah, I hope Anastasia was heard audible. But she's saying that the top one, because the bottom one is sort of keeping pace. This is sort of for those of you who drive. You ever get a creeping sense that the cars next to you are driving backwards? So you guys are driving at similar speeds, but the one next to you is just driving just a little slower. Maybe you're speeding, I don't know. But it's the opposite on the other side, right? Cars next to you, cars on the other side of the aisle seem to be moving really, really fast. And so you have this extra added motion to what you see in the sky. When the planet is on the other side of the sun, it seems to be going very fast. And when it's near you, it's much, much slower, and sometimes it stops, and sometimes it goes backwards. So Kepler says in this part, he agrees with Copernicus that this aspect of the speeding up and slowing down, and also the retrograde, is caused by the motion of the Earth. And this is very important for being able to actually separate the motions of all the different irregularities of what you see in the motions of the planets. Okay, so if that was clear. Let's come back to this one. So, okay, so Kepler wants to see if this hypothesis he made holds for this second inequality. And actually, there's a funny thing, which is that Copernicus actually says that the sun doesn't move, but that throughout, over time, the mean sun, which is basically the Earth's orbit, does change. And Kepler has this funny quip of, if you're going to make something the center of the universe, shouldn't you make the thing that doesn't make it the thing that is not moving? Anyway, so I did not realize that, if the technically, because the Earth, it does move, and Earth's orbit also changes, that you don't really divest the motions of their first inequality, or of the second inequality, when you take opposition from the mean sun. It's still very connected to the Earth. Anyway, I just realized that he doesn't say that explicitly. Okay, so what Kepler points out is this what he wants to see is what he wants to figure out. Okay, so first of all, actually, let me get rid of this drawing because it's not including something very important. Okay, so can we have, okay, I'm almost done here. Oh. What? Why can't you?
I think you're still layer 4.
Oh, I see. Thank you. Okay, so orbit of Mars, very important in dealing with the second inequality, is the orbit of Earth. Actually, I'm going to draw a little differently. Orbit of Earth. Okay, so like I said, the second inequality has to do with Earth. Here's Earth. Here's Earth's orbit, at least. And there is the, what did I do? Okay, it's a little switched around here. Here's the sun. Here's the center of Earth's orbit, the mean sun. Oh, I think I did that right. No. Here's the sun. Oh, actually, I want to point out something. So actually, after I figure this out, okay. So here's the sun. Here is the this is Mars's equant. And here's the line of apsides for Mars. Here's a funny thing he says. He says, this is the aphelion, which is the farthest distance from the sun. Because earlier, when we had this other one that went through the mean sun, this one here, this one was actually the apogee, because it's the closest with respect to Earth. Anyway, it's not the main point, but I thought that was funny. Okay, so then he has this system. Okay. Let me just make sure I have this right here. Yeah. Yeah, okay. Here's the center of Mars's orbit. And so, which is this bigger thing. And he wants to see, again, now he wants to see where Earth, not the sun this time, but where Earth is gonna see the biggest difference between the system that's based around the sun and the system that's based around the mean sun. So again, there's one that's based around this middle point, and there's one that's based around this middle point, which is the point. So there's a middle point that's between the sun and the equant, and there's a middle point that's between the mean sun and the equant. These are two different points. One of them is going to be, say, this one, and another one is going to be, say, this one. Sorry. It's relatively just sort of down. So he points out that there's one place which may see the biggest difference, and it's going to be well, the biggest difference in the sort of planetary orbits is going to be right here, basically. Because you just shoved everything down, and this is just going to be equal to the difference in the centers. And he wants to know where along this orbit, the Earth's orbit, the Earth is going to see the biggest difference between these two systems. And I'm not going to go through this part. Jason has a great animation on the website which shows you how to figure this out. Kepler has about 3 pages on this. He says it's right about here. that the Earth sees the biggest difference. You know, it can't be here. Obviously, this would be 0 at the very bottom. At the very top, it's 0, and then it fluctuates in between. People see that? If it's right above anywhere, you're going to see that difference to be 0. So he finds this difference. It happens to be the circle that just kisses the Earth's orbit, and also goes through those 2 points. And he finds that this angle here is, I didn't actually write it down, did I? Something very big. It's over a degree. Jason, what is it? 1 degree, 3 minutes, and 32 seconds. Wowza.
Extremely precise.
I know, it's funny because the footnote on this is, my calculation, the translator's footnote is, my calculation is actually 55 seconds. But it doesn't change the weight of his argument. And so, this is now observationally different. So from the Earth, this is going to make a big difference. Using the apparent sun versus using the mean sun was sort of equivalent for the first inequality, but it is not equivalent for the second inequality. It will be observationally different. And so this is very important because now Kepler is set up to say, okay, I can do this experiment. I can show you that your system will be wrong if you use the apparent motion, if you use the real sun, and I've set up a sort of a crucial experiment. I've set up a real experiment that can be observationally confirmed. Okay, so.
Leona,
yeah.
so I guess we have 2 sort of related questions.
Okay.
Schwach is asking again, how did he determine that it was at that point in the Earth's orbit that was the greatest difference from the standpoint of the Earth? What was the method he used to figure that out?
Okay, so I'm going to show you a great animation. I'm pulling it up right now, which Jason made, and it's not going to solve all your problems because it's actually why I had you guys do that homework problem, which is that the angle from any point on the edge of a circle, whose vertex is at any point on the edge of the circle, is half of that same arc from the center of that circle. So let's see here. So this is linked from chapter 6 page. It says, why put new there? So why put the Earth there? And this is a good, I don't know if Kepler did this, but this is a good visual of a continuous transformation that shows you what happens. You can see that as it's, the angle is 0 starting at the very bottom, right above the 2 points. And then it goes to 0 at the top as well. And somewhere in between. So first, we know that somewhere in between it's the largest. He has a construction which ends up solving for this angle here, which is the angle at psi. Yeah, I'm just not going to go into that. It's just too long. But this is a good visual. It's actually it is a fun construction. You learn a lot of geometry from it. But this is, for those of you who did this proof, but only for the angle, only for the angle from just opposite of the arc. To use it for this, you actually have to prove that the angle from any point on the circumference is equal to that angle that you proved it for. And I don't know if that made any sense to you. Let me see if I can show somebody's great picture drawing. Can you get, I wonder if they see this. I don't think they do.
You didn't take it off of the screen share?
No, I didn't. Okay. So somebody's great drawing is here somewhere. Hold on a second. Okay, so this is one of them. Here we go. Okay. Oh, you were already sharing. This one? This one.
That's the third
This one?
Yeah.
Okay. So, people see that? Or are you still looking at me? Okay, yeah. So that's, the one that I gave you is one particular case study, which is that an angle from the edge is always half of the angle formed from the edge to an arc is always half of that another angle formed from the center to that same arc. And now for those of you who just proved this case, or the equal case when the two isosceles triangles are equal, you have to generalize it now to that this angle can be formed from anywhere on the circle at all, and that they'll be equivalent. So you can form it from here, for example. And I think 2 people did that general proof. The other thing that I did not ask people to do, but I think he actually requires it, and you'll need it anyway later, is to be able to find a circle that that fits 3 points. Any 3 points. You take any 3 points and find a circle that fits it. So I don't know if that answers your question at all. Probably doesn't. It's in the book.
Well, I guess the other question, that is helpful, but the other question was on the homework on part 4, when we were playing around with that flash animation.
Right.
What would have been the best answer on that?
I was just about to show you. Yeah, that's a good question. So let me switch over to that. And just about everybody got this one wrong. So, and there's really, unless you had already looked at that animation, the animation that I just showed you prior to this, I don't know if you could see it. It's not really observationally visible. Okay, so in this animation now, let's see, who should we take? Let's take Copernicus's. I paused it. Let's do, okay, paused it. So I asked you to push I's information, and it says, you saw that the equivalence of hypothesis, these animations make the equivalence of hypothesis much clearer. You can move from one system to another. You can, okay, here's, the switch between mean and apparent sun models is done as in chapter 5, where the same equant is kept for both. By holding down the M key, you can see the flicker between mean and apparent sun models. To recreate the experiments, Kepler suggests in 5 and 6. Where is the biggest difference that the sun would see between the 2 planets? That the sun would see between the 2 planets, and how about the Earth? So let's go back, and M, he said. So let's progress a little. Okay, so you sort of see the difference between the planet is changing. What you should be looking for, probably could have hinted at, is here. How is the appearance changing? So already, to the sun, this is different, right? But to the Earth, the appearance is also different. And this is, to the Earth, the appearance is more different, as Kepler just proved. So I'm going to move around a couple different places, oops, and see if you can tell the difference. So people see that the Mars is changing positions, right? Now remember that when we went to these different models, that did not change these are very, very different models, and yet that did not at all change the observations. But this is changing it. Okay, so let's move along a little bit, and you'll see that, oops. So like here, I'm toggling again between mean and apparent suns, and Mars is barely moving. It's basically not moving. It's not different here. So I'm going to move a little bit more. So this is one way you could do it, is sort of just testing out and maybe zeroing in on what do you call it? Narrowing in on where it could be. Oops. What is going on here? Oh, here we go. Okay, again, no difference. Okay, so this is very different. Now, I'm just going to let it progress a little bit. Goes into, you see that it goes into retrograde motion.
Mm-hmm.
This is a lot. I mean, really, it's very hard to see. The answer actually is what we were just looking at, which is that particular setup, which is like right around here. Oh, anyway, it doesn't. This is pretty big right here. See that? It's like half of a Mars ball there. So that's sort of what you were. I only expected people to say that it changes, and that it's generally bigger or lesser in one place. You're not going to say, it's at when Earth is about 45 degrees from the line of apsides. Anyway, so that's that.
So you're saying that the bottom right, it stays the same whether you go to Copernicus, Brahe.
Yep. That's the equivalence. So-called sun-centered, Earth-centered, sun and Earth-centered. They're all the same. But not if you change the apparent sun to the real sun versus the mean sun. Okay. I had a couple funny quip answers to that one. Some of you know who you are, including the answer, I saw instructions pop up. All right. Were there any other questions? Um, Otherwise, I just want to go through a little bit of the homework. Just, some people actually did some pretty good things. I like the pictures that were sent in. That was very appropriate. Most people got the calculations right. Some people had some problems. If you cannot convert into decimal, it would actually help you. Well, it would help you because a decimal system it's 10 based, and the degree system is 60 based. So you end up having to do double conversion. Whether you notice that or not, I don't know. But you can just stick with the 60 base, then it'll make it easier on you. Number 4, I talked about. I guess that's it. That's pretty much it. There'll be a couple more homework problems. I mean, geometry problems. You end up having to do double conversion. Whether you notice that or not, I don't know. But you can just stick with 60 base, and it'll make it easier on you. Number 4, I talked about.
No, it's Steve.
Oh. Are you trying to ask something, Steve? I can't tell if I muted him or unmuted him. Mute? That's mute. Anyway.
Liona, for this homework, is it possible for you to send out a completed version with pictures?
A completed version with pictures? You mean an answer page?
Yeah. Or whatever you would have liked to have received on it.
Oh, you want me to show you one?
Yeah.
I have everybody's collected. Let's see here. This is it. People see that? Yeah, okay. So, I think Ian had done this general proof, which was very beautiful, of that problem. So basically an angle formed from any point on the circle. And most people just, took pictures. That's the very special case here of if the isosceles triangles are equal, which most people did. And then this is the complicated, but I guess true one that Seattle did. It was sent in twice, and then Cameron actually did screenshots, which I like. This is a good idea. Oh, this is camera. This is actually a camera shot. There's more geometry. I don't know what this one was made of. Maybe
Camera.
paint.net. And that was it, I think. Oh, and then there's these very pretty drawings. That's that. And it's good because with these things, everybody has a different proof. Okay, then if there's no more other questions, I just have a little thing to say about sort of the whole chapter or the whole book. Okay. Just interrupt. If you're saying something, I can't hear you. for now. But yeah, I would just come up with different examples of things hypotheses which really need this type of scientific rigor. And again, it's not really, it's not scientific rigor from the standpoint of details. Kepler does have that. He does go through the details. But he has a hypothesis. And I'll give you two examples that I thought of, and maybe that'll become clear what I'm thinking. So one example I thought of was environmentalism. So this is the whole CO2 is causing everything, right? Everything changing because of CO2. And first of all, I thought that was a funny comparison because it's very Earth-centered. It's a very Earth-centered system. And so that was just happened to be a good correlation that we wanted to bring that to a sun-centered system. But so one, the equivalence of hypotheses. So how are all the different hypotheses actually the same? And what are the foundations, what are the assumptions that make them the same? So you could have people like, for example, that think that CO2 is causing global something changing. Water, suppose water is the biggest greenhouse gas. The water is causing everything. And so on. And so just sort of thinks a problem like that through and basically not get caught up in one system or another. Figure out actually is there an equivalence? Is there a basic assumption that is between all the different systems? And how do you think of a sort of a crucial experiment that can bring it out? And some of these we played with as far as, like, for example, if you were to do a treatise like this on global warming, I would think that you would take the first book to disprove all the different weird models, and then whether it's like the SALT model or whatever, and then you would finally open it up for what is actually out there, which is the fun part, right? So would you set up, like we said, seismometers on Mars, or would you set up cosmic radiation instruments on Jupiter or something? Sort of open it up for a real investigation about what's really happening. So that was one example I could think of. Another one was something that Ben, I think, is going to go through pretty soon in great detail, which is the galaxies and black holes. So there's this really funny hypothesis about black holes. Now, they were created, according to what I understand of what Ben said. I personally haven't looked at them. But black holes were supposedly created to sort of balance out the fact that galaxies move in a way that they shouldn't move. They move faster in different places where they shouldn't do it. And so they've placed this thing, which Ben called it this halo of black holes, right? Or dark matter.
Dark matter.
It's dark matter, I'm sorry. Yeah, it's dark matter. So they place this halo of dark matter in order to balance out the gravity that doesn't exist, or that is unaccounted for. And this halo is really, really big. It's sort of bigger than the galaxy itself, much, much bigger than the galaxy itself, and so on. And so you can ask, well, there's various hypotheses that sort of edge it around, but I was asking myself, and you can ask yourself, how would you approach that problem that's not just sort of saying, "Oh, that's just absurd." You know, that's not really. That's not constructive. In other words. Okay, yeah, it sounds absurd, but that's how do you get further than that? And the other one I mentioned was the liberal versus conservative. It's another one to think about. Otherwise, in book 2, you're to look to actually breaking out of all the system altogether. So remember, so far everything's been pretty much the same. You still have an equant, an equalizing position, you still have circles, and so on. The only thing you've changed is the sun. And that's very important because now the sun does things. It doesn't just sit there like a couch potato, as Jason said. But now you're actually going to start crafting a real system. So the homework is on the same document. It's the same link. Oh, I can post it again. But the same link is just below the previous homework. And you guys will see Ben next week. Any last thoughts? Ideas, comments, complaints?
Yeah, we lost our connection for a second, but one thing we were talking about when we were reading is how absurd it is that Copernicus is considered, you know, the godfather of the heliocentric model, but he takes all of his data from the mean sun, which is actually based off of the Earth. So, anyways, that was one thing that struck us while we were reading.
Mm-hmm. Okay. Good. All right. Well, thank you for joining.
Well, one thing on the proofs is that the simpler the proofs, the better. I was noticing that some of the proofs for the doubling for the special case, to prove that the special case of the point along the circumference was twice the angle value of the angle made at the center. I saw that some of them were a lot simpler than the ones I did, and I think just in general it's important to keep the proofs as simple as possible.
Yeah, it's fun to see all the different proofs. I guess, do people want to see everybody's homework?
You can email it out.
Are you okay with your own homework being seen by everybody?
Yes.
Yeah, the NSA already sees it.
And they're not learning anything from it, so. All right, I'll share the document then. I just put everybody's, because they were coming into different email boxes, so I put everybody's homework, copy and paste it into a Google Doc. And so I can share that with you. I think only one other person did, or maybe 2 other people did a general proof. But maybe I'm wrong. I didn't. Good. Yeah. I didn't get a chance to respond to all your homeworks yet. I'll do that tonight. Okay. Join us next week.
Bye.